Hello, this is Modumath Tape 3.1. The subject is Understanding Decimal Fractions. Modumath Text 3.1 goes with the tape. Open to this text now. Keep pencil and paper handy to solve problems and take notes. If you have any questions, either about the material or the machine, ask someone to help you. Decimals have many uses in all of mathematics, but we'll be interested in them chiefly as a shortcut in working with fractions. For this reason, we often call them decimal fractions. Let's see how they can help us. You've just completed a unit on fractions. You know that adding, subtracting, or even comparing fractions is easy enough if they have the same denominator. But if the denominators are different, it could be quite a chore. You have to begin by finding a common denominator for all the fractions involved. Only then can you settle down to the arithmetic. The beauty of working with decimal fractions is that for all practical purposes, we can express fractions with just a few denominators, 10, 100, 1,000, or some other power of 10. The reason we choose these particular denominators rather than any others is that our whole way of writing numbers depends on the number 10. So sticking with powers of 10 makes the arithmetic very easy. This is why we work with decimal fractions. Let's see how we go about it. Let's return to the whole numbers. Look at the numbers shown, 444. You know that each of those 4s means something quite different. The one to the extreme left signifies 4 hundredths. The one next to it is only 1/10 as much. It signifies 4 tens. The 4 at the extreme right signifies only 1/10 of that. It means only 4 ones. Using exponents, this becomes 4 times 10 squared plus 4 times 10 to the first power plus 4 times 10 to the 0 power. We'll just call it 4. As we move from left to right, each 4 signifies 1/10 the value of the previous 4. As long as we knew only about whole numbers, we had to stop right there. But now that we know about fractions, numbers between the whole numbers, we can ask ourselves, what would happen if we continued the process? Let's begin by putting a little arrow to the right of the last 4, just so we can remember where we stopped. Now, let's note down still another 4. What can this 4 mean? We saw earlier that as we move from left to right, each of those 4s was 1/10 the previous 4. The pattern was 4 times 100, 4 times 10, 4 times 1, and that's where we stopped. What can be more reasonable than for this new 4 to mean 4 times 1/10? Or 4 over 10. As before, the new 4 has 1/10 the value of the previous 4. If we write down still another 4, we would expect the pattern to continue. The new 4 should signify 1/10 the value of the previous one. Well, the previous one signifies 4 times 1/10, or 4 over 10. 1/10 of that is 4 over 100, or 4 over 10 squared. Again, the entire number is shown in expanded notation. Still another 4 would represent 4 over 1,000, or 4 times 1 over 10 to the third power, and so on. This process could continue indefinitely. Now, you've probably seen numbers like this before, except that you're used to seeing a decimal point instead of the arrow. Okay, let's change the arrow to a decimal point. But it's a good idea to think of the decimal point as just that, a kind of pointer signaling where the unit's place is in the entire decimal. As we move left from the unit's place, the powers of 10 keep increasing one by one. As we move to the right, the powers of 10 appear in the denominator. 10 to the first, 10 to the second, 10 to the third, and so on. Let's look at another decimal number. The decimal point tells us that the 9 is in the unit's place. Working to the left and counting off places, we have units, tens, hundreds, and thousands. So that much of the decimal number means 7 times 1,000, plus 0 times 100, plus 5 times 10, plus 9 times 1. Or, in exponential notation, 7 times 10 cubed, plus 0 times 10 squared, plus 5 times 10 to the first power, plus 9. Working to the right, we can count off tenths, hundredths, and thousandths. So this part of the decimal number becomes 1/10 plus 5 hundredths plus 6 thousandths. This can also be written 1 times 1 over 10 plus 5 times 1 over 10 squared plus 6 times 1 over 10 cubed. Here's another decimal written in expanded notation. Let's go over it carefully. You'll soon be doing one yourself. This is 3 times 10 to the second power. That's 3 times 100, plus 8 times 10 to the first power, plus 7 times 10 to the 0 power, that's plain 7, plus 9 over 10 to the first power, plus 4 over 10 to the second power. Here's one for you to do. Write this decimal in exponential notation. Take your time and work carefully. You've got a full minute. If you like, use the one just shown as a pattern. Here's the correct answer. 4 times 10 to the second power, plus 5 times 10 to the first power, plus 6 times 10 to the 0 power, that's just 6, plus 7 over 10 to the first power, plus 8 over 10 to the second power. It's not easy to get this right the first time. There are more examples worked out in your Modumath text. If you had any trouble, go over them carefully. Otherwise, you're ready to go ahead. It's important to learn to read these decimals. For example, the illustration shown is read 287 and 5/10. Notice we use the word "and" only to signify the decimal point. We do not use the word "and" anyplace else in reading the decimal. The second number is read 316 and 9/10. The next example is a little different. We see 3, decimal point 09. So we may start off 3 and what? And 9 something or others, but we'd better make sure what they are. Well, let's look at this decimal in expanded notation. It's 3 plus 0/10 plus, and here's what we're looking for, 9/100. So what it's 9 of is the hundredths. Hundredths, not tenths. Where would the 9 be if we meant it to read tenths? It would be in the tenths place, as shown. But it's not. It's 3 and 9/100. Let's look at another one. Decimal point 007. This time, there's nothing to the left of the decimal point, so we can start right in with the fractions. It's 7 somethings, but we must make sure 7 watts. Again, we turn to the expanded notation. It's 0/10 plus 0/100 plus, here it comes, 7 thousandths. So the decimal is read simply 7 thousandths. Try a few yourself. When you say it, be sure to sound those th at the end of tenths, hundredths, thousandths. Okay, here they are. Read them. The first one is read 163 and 7/10. The second, 4 and 8/100. And the third, 21 and 9/1000. If you read them this way, you're really getting the idea. Remember, we use the word "and" only to indicate the position of the decimal point. Look at the decimal shown. In expanded notation, it's 25 plus 3/10 plus 8/100. Yet when we read it, as you probably know, it's 25 and 38/100. What happened here? What gives us the right to shift from 3/10 plus 8/100 to 38/100? Let's see. Have a closer look at 3/10 plus 8/100. Remember, it's always all right to multiply the numerator and denominator of a fraction by the same non-zero number. The value of the fraction isn't changed. Well, let's multiply numerator and denominator of 3/10 by 10. We now have 3 times 10 over 10 times 10, or 30 over 100. This gives us 30 over 100 plus 8 over 100. The 8/100 isn't changed. Now the denominators are the same. So, adding, we get 38 over 100. In other words, 3/10 plus 8/100 has exactly the same meaning as 38/100. It's as if you owed someone 38 cents. You could pay it in 3 dimes and 8 pennies, or you could pay it in 38 pennies. The amount of money is exactly the same. So we're on safe ground in shifting from 25 plus 3/10 plus 8/100 to 25 plus 38/100, which we read 25 and 38/100. The second form is certainly easier to say. Similarly, how do we read the decimal shown? In expanded notation, it's 2/10 plus 3/100 plus 9/1000. But we certainly don't want to say all that. So we rewrite all the fractions with the common denominator, 1,000, as shown, and add. The answer is 239 thousandths, which is how we say it. Changing a decimal to a fraction or a mixed number isn't much trouble. Some problems appear in your Modumath text labeled Exercise 1. Here, for example, we're given the decimal 73 and 12/100. The 73, which is also known as the whole number part of the decimal, is untouched. We don't do anything with it at all. As for .12, we replace it by the fraction to which it is equal, 12 over 100. So 73.12 becomes 73 and 12 over 100. We reduce this to lowest terms if we like. The answer is 73 and 3/25. The next example is 49.106. Again, we leave the 49 part untouched. The rest of the number is written in fractional form, 106 over 1,000, and reduced if we want to. In the third example, the whole number part of the decimal happens to equal 0. This doesn't change the procedure one bit. We are left with .25, which we write as 25 over 100, and reduce, if we like, to 1/4. Here are a few examples to try yourself. In each case, rewrite the decimal fraction as a mixed number, or ordinary fraction, and reduce to lowest terms. Compare your answers with those shown. If you had any difficulty, check your Modumath text or ask someone to help you. How about changing in the opposite direction? That is, changing a fraction to a decimal. So far, we can do this only if the given fraction has a denominator of 10, or 100, or 1,000, or some other power of 10. In that case, it's easy enough. A few examples are shown. As for other cases, they'll be considered in a later tape. Let's consider one more idea. You already know that, given any whole number, you can write zeros to the left of it. It may not serve any purpose, but it certainly doesn't change the value of the number. Let's see what happens if we put zeros to the right of a decimal. For example, here is the decimal 0.7, or 7/10. What happens if we write 2 zeros after it, turning it into the decimal 700 thousandths? Well, if we think of the decimal in expanded notation, it becomes 7 times 1/10 plus 0 times 1/100th plus 0 times 1,000th. So the sum of the three terms equals 7/10 plus 0 plus 0, or just plain 7/10. And this can be stated as a general rule. Suppose we have a decimal number, complete with a decimal point. For example, 4.21. We can always write more zeros as shown. The value of the decimal remains the same. Here's another example, 6 9/100ths. We write one extra zero, then another, then another. We can go on forever if we like. The meaning of the decimal isn't changed. Right now, all these extra zeros may strike you as silly, but they're important when we come to division of decimals. We should warn you that in science, when we weigh or measure something, those zeros have a different meaning. They indicate how carefully we've done our measuring. However, in mathematics, they don't mean a thing. Let's review the ideas of this tape. First, we saw that we could use the decimal point to signal the units place of a number, and then continue with digits to the right of the decimal point, signifying tenths, hundredths, and so on. Second, we learned to write these numbers in expanded notation. Next, we learned to read such numbers and to express them as mixed numbers or fractions. We also learned to express a fraction as a decimal, provided the denominator of the fraction was 10, 100, 1,000, or some other power of 10. Finally, we learned about putting in zeros to the right of a decimal. Now we know something about decimals. In the next few lessons, we'll learn to add, subtract, multiply, divide, and compare them. You'll see that in the main, these operations are easier than the same operations for fractions. And finally, when we've learned all that, we'll learn to replace any fraction by a decimal. The decimal will not necessarily equal the fraction, but for all practical purposes, it will come as close as necessary. When we've done all this, we'll be in a position to use decimals, which are easy to handle, in the place of fractions which are not. But that's looking far ahead. Meanwhile, if you think you understand this tape, go on to the problem session in your Modumath text.